Swayam Prabha. Digital India. Educated India.
Hi friends. So in the last module, we looked at the emotions in the GSR signal, a very popular physiological signal to observe the emotions. Now in this we will again look at a very common physiological signal and very popular, which has become very popular in the recent years, is the EEG signal, or as it is known as the electroencephalography signal. So you already know that our brain, it consists of millions of neurons, and it turns out that in order to communicate with each other, these neurons, they fire in sync in order to do the communication. So it turns out that whenever there is a firing of thousands of neurons together, then what happens, that they generate an electrical field which is strong enough to spread across tissue, bone, and more importantly the skull. And that is how we eventually measure the electrical activity of the brain on the head surface. So this is what essentially is EEG. So EEG is what? It records the electrical activity generated by the brain. And how it records? Of course, with the help of certain electrodes that we place on the scalp surface. So we will see some example. And so basically, as I was saying, that the reason that the neurons fire in the brain, because they want to communicate with each other via some electrical impulses. And this communication, it turns out that it's not a random communication that happens, of course. So these communications, they have been shown to be associated with certain cognitive processes, such as drowsiness, alertness, or in turn, that is what you call as a kind of engagement, how engaged you are. They give a sense of wakeful relaxation, that whether you are in a relaxed state, even though when you are awake. And then of course, more importantly, they also tell you about whether there is an approach or avoidance attitude in response to something by looking at your brain activity. So then, because of this reason, that we are able to understand, let's say, lots of emotional information about the individual, such as the engagement, such as the different cognitive states that an individual is in through the brain activity, and that is what it makes it very exciting. Other important feature about the EEG signal is that it provides an excellent time resolution. What it means, that first thing, the response time of the EEG signal is pretty fast, is somewhere around 200 milliseconds. So basically, from the onset of the stimulus, it takes around 200 milliseconds for the response to occur in the EEG signal, and hence it allows the detection of the activity at sub-second time scales. As I said, within milliseconds, within 200 milliseconds, you may have the response, and so within a second is a time scale itself, you can analyze the activity that is happening. Right? Activity in the sense, the cognitive activity that is happening inside the brain. So now, having understood that, let us try to understand how can we measure the EEG signal. So it turns out, again, it's not so due to the advancements in the wearable technologies. Now it is not so invasive sensor and tools that are used to analyze the brain activity. So basically, in this, what we do, we put the EEG electrodes, such as the one that you are seeing on the left screen here. So basically, this is a one diagram where we are looking at how do we do the EEG measurement. So basically, the EEG electrodes, this is what is the EEG electrodes, and these EEG electrodes, they are put on the scalp, surface of the scalp, using in the form of a EEG cap, just to make the life easier. When you are putting it in the form of the EEG cap, it makes the placements and all a bit easier. And then what happens, then whatever signal that is these electrodes are capturing, of course, it turns out that these are again very small minuscule voltages. Of course, because you are not a transformer, the human brain does not generate a lot of current or voltage, thankfully. So basically, whatever the voltage, whatever the electrical activity that the electrodes are capturing, then of course that electricity is usually passed through an amplifier, which then amplifies it, and then of course then it is sent for the further storage and for the further processing for each different electrode. So for example, here you can see that there are different number of waves, there are n number of waves. So for example, in this case this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically there are different number of waves that are representing the electrical activity as captured by the different electrodes. So for example, if there are 10 waves here, so basically they are representing the activities of 10 different electrodes, right? So as many number of electrodes you will have on the EEG cap, as many number of waves you will get for the further processing and for the further storage and the recording purposes. And it turns out that nowadays, as I said, because of the advancements in the wearable technology, there are many even more non-invasive and portable kind of headsets, such as this emotive epoch headset that you are seeing on the right side. So you can see that the EEG emotive epoch headset, it constitutes around 14 electrodes, and among those 14 electrodes you see that it's not a kind of in a cap structure, it's purely it is a Bluetooth headset. What it means that it simply captures the data through the electrodes, and then it simply makes use of the Bluetooth to transfer the signals in a wireless fashion to the nearby computer or wherever you are trying to collect the data. And it turns out that like all the 14 electrodes that are there is being depicted on the this particular diagram. So this is the locations of the electrode of the emotive epoch as per the 1020 international labeling system. So basically, in order to understand this thing, let us try to understand what is the electrode labeling 1020 system. So basically, this 1020 international system, it is a international system to label the placement of the electrodes in a uniform fashion. So basically what it has, as you can see on this diagram, it shows you the electrode locations of the international 1020 system for the EEG data. Now if you look at here, the electrode placements in general on the surface of the scalp is defined in certain different areas, such as prefrontal region. So for example, if you look at these two, so for example, basically this part is what is known as the prefrontal region of the surface. Similarly, then you have the frontal region. So it's not hard to imagine that why this becomes the frontal region. So basically prefrontal, and then you have the frontal region of the scalp. Similarly, you have the temporal region. So basically this is what is the temporal region of the scalp. Then you have the parietal region. So basically this is what is the parietal region. You can very well imagine this is the parietal region. And then you have the occipital region. So basically occipital region is at the back, and then of course you have the central region, and then that is what are the different regions in which the placement site on the surface is divided as per the 1020 international system. Now apart from this placement regions, there is a zero that is often attached with the electrode, and the zero refers to as the midline sagittal plane of the skull. So for example, if you look at this midline sagittal plane, that is what refers to the electrodes that are placed on this midline sagittal plane, and then accordingly the F becomes FZ. So electrodes placed on the frontal cortex, they become the FZ. Similarly on the central, they become CZ. Similarly on the parietal region becomes the PZ, right? And mostly the electrodes that are FZ, CZ and PZ, they are mostly for the reference or the measurement points. So their data is not used in the analysis, but rather it is used to understand the baseline or understand the reference points of the EEG data, right? Now it turns out that as per the structure, as per this labeling system, the even numbered electrodes such as 2, 4, 8, 6 and so on and so forth, they refer to the electrodes placed on the right side of the head. Similarly, right? So these are the even numbered electrodes. They refer to the electrodes placed on the right side. Similarly, the odd numbers such as these, they refer to the electrodes placed on the left side of the human the scalp, right? So skull. So that is how is the placement of the 1020 system looks like. Now, of course, like these are not the only the number of the electrodes that can be represented, you can have in a EG system. Of course, you can have very well even 128 or even up to 256 electrode systems are very popular, well, are common, not so uncommon to have, but nevertheless you can imagine the more the number of the electrodes, the more the density increases, and hence what we call it as the spatial resolution increases with the more number of electrodes. We will talk about the spatial resolution in a bit, and of course you can very well imagine that with this what happens, and that the precision of the data that you get, it increases. Nevertheless, also it adds to the cost, it adds to the more intrusiveness, it adds to the complexity of so many different things, right? So now having understood the 1020 system, let us try to look at the electrode locations for the emotive epoch. So if you look at this thing, so you have this AF3 and the AF4. What is this? Basically these are representing the prefrontal cortex, prefrontal electrodes. Similarly, you have these frontal electrodes, right? These are the frontal electrodes, but which are more related to the central parietal. Similarly, you have the temporal electrodes. These are the reference point electrodes. Similarly, you have the electrodes in the parietal region, and these are the electrodes in the occipital region, right? So that is how altogether you have 14 electrodes in the emotive epoch system, which is a nice system. It's a portable system, it's a wireless system, and on the other hand, you can always have this kind of a the EG caps that you are seeing on the left hand side. So nevertheless, no matter what type of device you have, all these types of device, they make use of usually this international 1020 system for the placement of the electrodes on the surface. And it turns out that all these different regions of the human brain, they represent the information about different areas, right? So without going too much into the neuroscience, we will simply try to now look at the different features of the EG signals that are related or correlated with the emotions, rather than trying to understand the EG data as such, right? So basically one of the very popular feature with respect to the EG signal is known as the frontal alpha asymmetry. So the frontal alpha asymmetry, as the name itself suggests, basically this is what? This is the difference between the right and the left alpha activity over the frontal region. So let us try to break it down. So basically this is what? This is the difference between the right and the left. So basically you have, of course, you have a right hemisphere and you have a left hemisphere. Not hard to understand. Over the frontal regions. So we already understand there is a prefrontal cortex and there is a frontal region. So basically what you have, of course, alpha activity we will try to understand in a bit. Basically what it says, that it says the difference between the frequency power over the left and the right frontal regions, and we talk about the left and the right frontal regions. So basically you have several options. You can have either the F3 or F4 as a pair, F4 representing the right hemisphere, F3 representing the left hemisphere, or you can even have the F8 and the F7, right? So basically you can have a pair of these two, or you can have a pair of these two, and in turn what you try to do, whenever you take the difference between the spectrum power of these electrodes, that is what is known as the frontal alpha asymmetry. Now where does the alpha comes from? You already understood the frontal, you already understood the asymmetry, basically the difference between the frequency power, between the band power. Now alpha, where does the alpha come from? So let us try to so alpha is basically, it turns out that the EG signal, it can be categorized into the different bands as per the frequency ranges that it has. And so basically roughly speaking, we have this we call this delta. Delta is the frequency band that is representing the 1 to 4 hertz commonly, and basically this particular region, it represents the electrical activity when an individual is in the deep sleep state. Similarly you have the theta. So basically this is what? This is representing the deep sleep state. Similarly you have the 4/8. So basically 4/8 is what? 4/8 is known as the theta region, and this theta region, basically theta region, the activity in this theta region, that is the electrical activity within the 4 to 8 hertz of the EG signal, it mostly represents the drowsiness, and it also represents your condition, let's say when you are doing the meditation, right? Similarly then you have the 8 to 10 hertz. So basically 8 to 10 hertz and this 8 to 12 hertz. these two are combinedly, this is known as the alpha band. And basically in the alpha band, it is basically the activity, electrical activity of the brain when mostly you are in the relaxing state, and many times when you have this closed eyes, right. So basically that is what is the these two are representing together. And then you have the beta band. So basically beta band is the electrical activity that happens between 12 to 30 hertz, and this beta band, it mostly represents when you are in the state of, let's say, concentration, or when you are doing thinking. So it represents the concentration and the thinking. Similarly, when you look at the 30 to 60 hertz, this is the gamma band, and in the gamma band basically what it represents different cognitive functions, including the workload, cognitive workload that you may be experiencing, right. So these are the different bands in which corresponds to the different sets of activities that the individual is involved in, at least with respect to the cognitive state, right. So having understood that, now let us try to so now you may have understood that, okay, what is the alpha activity? So basically alpha activity is what you are trying to look at, the frequency power in the alpha band. Alpha band is the 8 to 12 hertz frequency, roughly speaking, right. So basically you are looking at the difference between the F3 or F4 or F7 or F8, but of what? Of this 8 to 12 hertz frequency power for the EEG signal. It's not hard to understand. Again, frontal is the frontal electrode, asymmetry is the difference, and then alpha is basically you are looking at the alpha activity, the 8 to 12 hertz. And then when you talk about the frontal pair, there are on two usually you take two pairs, two sets of possibilities are there. Either you take the F3 or F4, or you take the F7 and F8, right. And it turns out that this frontal alpha asymmetry, it is used as a proxy for the feelings of approach or the avoidance. What it means? So when you are looking at an stimuli, when you are looking at an activity, or when there is an external event towards which you are feeling engaged, or you are feeling as more interested, so you are approaching that, and then so that particular experience, or in the same way the experience of when you are feeling boredom, when you are withdrawing from the interest of a particular activity or an stimuli, that is being represented by the FAA signal, right. And as I said, so mostly we use the alpha band here, but many a times this gamma band, which is the greater than 30, and this beta bands are also equally used, but more importantly this FAA is the most commonly used activity. Now there is an interesting phenomena here, that it turns out that there is an inverse relationship that exists between the alpha band power and the cortical activity. What it simply means that if there is more brain activity happening, then there is less alpha power, and vice versa. It means when there is more alpha power, it means there is less brain activity happening. So I hope that this is clear. Again, I will repeat that when there is more brain activity happening, when your brain is actively involved in something, or when a particular part of your reason is of your brain is actively involved, then you will find that the alpha power for that particular reason is less, and vice versa. So now if you combine these two, what it means? It simply means that when there is an increased left frontal activity, when there is an increased left frontal activity, what it means that it serves as an index of the approach or the motivation or the related emotion, right. So increased left frontal activity, it means you will have less alpha power here. When you have less alpha power in the left in the left frontal region, it means that you are feeling an approach motivation, or let's say related motivation, which in this case could be of the anger as well, which is an exception when it comes to the positive emotions. Similarly, when there is a relatively increased right frontal activity, which means when you have a less alpha power in the right frontal region, then it means that there is a withdrawal motivation. Withdrawal motivation, so you are sort of experiencing a negative emotion, and then you are trying to withdraw from the stimuli or from the event, which is in turn representing that you are feeling disgust, fear, sadness, and so on, so forth, right. So now you can see how beautifully the frontal alpha asymmetry, again I will summarize it. So basically the frontal alpha asymmetry, it is used as a proxy or as an indicator of approach or withdrawn or approach or avoidance. In order to calculate the frontal alpha asymmetry, you simply look at the alpha band power, that is the band power that is the power in the range of 8 to 12 hertz in the F3 region or F4 region or F7 region and F8 region. You take any of two pairs and then you simply take what is the band power there, and if you have an increased left frontal activity, which means you have less alpha power here, then it means there is an approach motivation, there is usually a positive emotion. Of course anger is an exception here, you may be experiencing anger also. And when we have increased right frontal activity, means when you have less alpha power in either F4 or F8, then it means that you are experiencing a negative emotion, which is an indicator of the withdrawal motivation or for example disgust, fear or sadness, right? So this is a very important feature that you may want to look at, and it turns out that it has been very commonly used in trying to understand whether you are liking something or for example whether you are disliking something, right? And quite easy to calculate. Now apart from these frontal alpha asymmetry, there are different there are other features that are very popular. Of course again you have to understand this is again a time series signal. So when you have a time series signal, you can do the analysis in the time domain, you can do the analysis again in the frequency domain, you can do the analysis in the time frequency domain, and so on so forth. So basically it turns out that the way we have event related potentials or event related skin conductance response for the GSR signal, in the same way we have the event related potentials in the EG signal, and there are different types of ERPs that we have for the EG signals. And for example one that is very popular, which is also known as the P300. What it means, so basically the number 300 here, it represents that there is a response within 300 millisecond from the onset of the stimuli, right? So that is what is for example the event related potential, and again you can calculate lots of statistical feature on it, and the domain or the community uses lots of statistical features on this P300. Similarly, as I was suggesting, you can definitely use the power features from the different frequency bands. You already know that there are different frequency bands for the EG signal, and then within those different frequency bands you can simply calculate the power, and then using those power you can understand what exactly is happening in that particular region, right? So that is the power feature from the different frequency bands. And then it turns out that there is a very interesting paper that for example there is a very interesting paper which was presented by researchers in 2014 which nicely represents that what are the different features that are related to the EG signal in response for the emotion recognition. And then it turns out that they have shown that for example advanced features such as higher order crossing. So for example if you look at this is what is representing the higher order crossing. So for example higher order crossing is what? Higher order crossing is simply the number of times the waveform is crossing the axis, right? So basically you count the number of times the waveform is crossing the axis and you take some differences, you take the difference of that, right? So basically this HOC is for example what the researchers have shown here, that this HOC, this is the weightage, sort of it is representing the weightage in among the different features when it comes to for the emotion recognition. So you can see that these advanced features like the HOC for example is outperforming the commonly used, for example the power band features. So this is what is representing the power band features, and similarly it is even outperforming many different features which are even including, let's say these are the DW2 features, which is discrete wavelet transform features. Similarly for example there is either this statistical feature and so on so forth. So without going too much in detail, again here you can see that here in this particular paper the researchers have tried to analyze and understand the different features of the EG signal in time domain, again in frequency domain, and again in the time frequency domain. And then if you look at this particular diagram, it gives you a very nice representation about the weightage or the importance of different EG features with respect to the emotion recognition. I will definitely invite the audience which are going to look at the emotion recognition from the EG signals to have a look at this very interesting and nice article. Perfect. So now we have already understood about the EEG signal, and then we already are a bit excited. I hope that we are a bit excited about the use of the EEG signals. So with that, we have to also understand that there are certain limitations again associated with the EEG signals. So one limitation that is associated with the, and it is very common with the EEG signal, that it has a very poor spatial resolution. What it means, that while it has an excellent temporal resolution, it is very fast responsive signal, and within 200 milliseconds it can give you the response to an external event or the stimuli. You really do not know that whether the signal that is being produced is produced near the surface, that is from the cortex, or it is being produced at a much deeper level. So basically, there are different ways to, and this is what we call it as the source localization problem in EEG domain. To address this source localization problem, of course, one way that you may have rightly guessed, that is to make use of multiple electrodes. But now you can understand, the more you have the number of electrodes, of course, it sort of gives you a hint, but then also there is no proper way to understand this source localization, or to resolve this spatial resolution for the EEG signal. Nevertheless, I think it is also very easy to understand that while there is availability of the portable and the mobile portable and non-intrusive devices, wireless devices such as EMO-TV POC, and there are others also in the market, it's a bit intrusive. Actually, it's a bit intrusive in comparison to the GSR and the heart rate sensors that we saw earlier. Nevertheless, it provides an excellent time resolution. It's a very effective sensor. But to handle this, again, you need some sort of training, about how to do the placement of the electrodes on the human skull, and then at the same time, how to perform the analysis of the signal that you are capturing. It requires a bit of understanding of the signal processing in order to understand how to do the analysis. Of course, but bottom line is, nowadays there are lots of tools which are available online, and then at the end, as I said, like, we will have a demo of certain tools, certain methodologies, which will definitely help you a lot in doing the pre-processing or in doing the analysis of these physiological signals. So you need not to worry about it. Of course, it's always good to have a background in the signal processing for this thing. One very important problem that is associated with the EEG data, that is, it is almost always contaminated by certain artifacts, such as the electrical signals which is detected along the scalp of an EEG. So for example, if as simple as that, so when you are capturing the EEG signals, as many times there is going to be a blink or an activity in the eyes, in the eyes, it is going to be reflected as an artifact in the EEG signal. So you have to understand that when these artifacts are occurring, and of course accordingly how to remove them. Again, it turns out there are tools which can do this job for you. Again, as I said, so EEG, while it's a very interesting signal to have, and it gives you a lot of information, many a times EEG signal again is combined with the facial expression analysis and the eye tracking to have a multi-modal view of the emotion that we're trying to analyze and understand. Right. So now we already understood about the emotions in the EEG signals. So let us try to conclude, and after that we will go for a demo on the how to process and analyze the physiological signals. So it turns out, of course, what we understood first, that physiological sensing is an important tool for the affective computing community. More importantly, because it gives you unaltered form of the emotion. It cannot be faked, and hence it is sort of represents the pure emotions that are occurring in the humans. Other important thing, that physiological sensing, in contrast to other form of sensing that is available, it allows you to have continuous and discrete monitoring of the individual's emotional state, right? So basically, when you are trying to analyze let's say when you are using the self-reporting to understand the emotional state, you cannot really do a continuous monitoring over there, right? So you cannot really ask every second, every millisecond that, okay, how are you feeling, and so on and so forth, what is your emotional state, right? But it turns out, if you have the sensors which are wearable, which are portable, which are wireless, then of course you can, with the help of those sensors, you can really do a continuous monitoring of the emotional state. Among the different physiological signals, what we also saw that the heart rate, GSR and the EEG signals are the signals which are most commonly used for the emotion recognition and the emotion analysis. And with this, like among these physiological signals comes lots of challenges, such as, of course, one we talked about the labeling or the annotations. So we saw that, okay, in the wild the onset of an emotion is often unclear, while when you have a very laboratory settings, lab like conditions, you have a lot of control, you can really mark when the stimulus is being presented, when there is an onset of the stimulus, but there is usually not much resources available when you want to do these experiments, when you want to collect the data in the wild. And then for the same reason, there is something known as windowing here. So window based approach. So basically in the window based approach, what you do, basically rather than trying to analyze the signal every second, let's say, or every minute, you create a window of, let's say, 5 seconds, 5 minutes or something like that, and you try to analyze the emotion within that particular window, and then you sort of moving window, you make use of a moving window, and then you, let's say, if there is a 5-minute window, you move it with 50% interval. So then the first signal that will appear from the 1 to 5, similarly the second signal, if there is a 50% overlap, may appear from 2.5 to, let's say, 7.5 and so on and so forth. So you got the idea, right? So this is known as a 50% overlap of moving window. So you try to analyze this emotions in a window segments, and then you try to do this moving window to capture to help you analyze the emotions without even precisely knowing the onset of the emotions. So of course, the problem is the subjective self-perception of the emotion. So what I mean by the subjective self-perception of the emotion, that of course, whenever you want to analyze the emotions, you need to get the ground truth of the emotions from the humans only. And then it turns out that the emotions are very, very subjective. So the same thing one individual may feel happy about, another individual may feel sad about, and then it turns out that emotions itself are very, very complex. And then there are, of course, well-defined emotion models, but then you really need to make the participants understand those emotion models like in advance, and to whatever extent you can, so that they can give you a good perception of the emotion in terms of the models that you are trying to analyze or use. And this is something that is not let's say specific to the physiological signals, but it is common to all other modalities as well. This is interesting actually. So basically, apart from this thing, like it turns out that there is many to one mapping of the non-emotional and the emotional influences on the physiology. What it simply means that, for example, while there may be response in the physiological signals in response to an emotional stimuli, the same type of response in the physiological signals may also happen due to some physiological some physical activity as well. So for example, as simple as that, if I sneeze at a moment, at this moment right now, maybe just my sneezing itself will increase my heart rate to a certain extent, and it will make some changes in my physiology, which may not be related to the emotional state that I'm feeling, or it will not relate it will not be associated with the emotional state that I'm in, right? So and it turns out that there is a many to one mapping here. So basically, you have non-emotional actions, you have emotional influences, and for the non-emotional and the emotional influences, you may have same sort of physiological responses. And it turns out that it's a bit tricky problem when you want to analyze the emotions in the wild. Of course, that is here, people have used for example, people have used different types of sensors again to understand how to differentiate among these two. And one very popular kind of sensor is the for example, IMU sensor, which is the inertial measurement unit sensor. So basically, the IMU sensors, what they do, they try to observe the emotions, the motions of the human body while you are trying to observe the emotions, making use of the physiological signals. So of course, when there is a motion detected by the EMU, maybe you may not want to consider the physiological responses in that particular segment, right? Or you may want to be a bit careful while analyzing that. So that is one very important and interesting challenge that we have. Again, one challenge that is very, very common across all the modalities, and maybe a bit more pronounced in case of physiological signals, is the individual variability. So What is individual variability? So basically individual variability is as simple as that there are variations in the individual's expression of physiological signals. As simple as that. For example, your baseline heart rate may not be the same as someone else's baseline heart rate, right? So for example, there is a range usually even for the healthy individuals. If I'm not wrong, the heart rate, the healthy heart rate looks like 60 to 72 beats per minute. So there is a reason that there is a range, right? So because there is an individual variability, 65 is also okay, 70 is also okay, 60 is also okay. And so it turns out that you need to know this variability, the baseline for the individuals, in order to understand what is the change in the physiological activity for that particular individual in that particular sensor or signal, right? So this is also very interesting limitation that is there. But nevertheless, bottom line is like there is a lot of research and lot of work development that is being done with respect to the analysis of the emotions in the physiological signals, and it turns out that with the proper endeavor, right, so with the proper efforts, it turns out that if you are looking at the right sensor, if you are looking at the right setting, and if you are looking at the right type of analysis and machine learning and deep learning and signal processing techniques, then these physiological signals can enable very effective can enable effective computing in a very robust fashion, which is private. Of course, you are not in many senses the data of the individual is private. You are not it's kind of anonymized. You are not really looking at the identity of an individual, so that is, in that sense, it's quite private. Of course, it's quite personal, again for the same reasons. You are not trying to identify the individuals in that case, rather than you are simply trying to identify the emotions that individual is having. And other thing that is very important, and that is not offered by so many different modalities, is that you can do the analysis of the emotions in a continuous fashion, which is not possible with the several of the other modalities. And it turns out that it is a luxury when you combine this private, personal, and the continuous method attributes together, right? So with that, then there are lots of references that we used while trying to come up with this lecture, but that is all. Of course, we will provide the references to you, and now we will try to look at the demo that we was talking about, that how to do the processing or the analysis of let's say a particular physiological signal to understand the acquisition, pre-processing, maybe feature engineering, and then the classification. Okay, so with that, see you at the demo. Thanks.